Hi, welcome to the final stage of the Mitsuru Yamada SAR ADC. This project is inspired and the design is taken from Mitsuru Yamada's Hackaday project, the link to which is included in the description. So this stage of the project is fully able to convert an analog voltage from a potentiometer into a binary output, and there's also an added component which makes this project I2C compatible using this Arduino Nano. So here's a quick demonstration. Right now, I'm going to flip the switch and the circuit is in manual mode. This means that I have to press this button in order for the output to update. So if I dial the potentiometer to a random value and click the button, the voltage is approximated onto these LEDs. This is the MSB and this is the LSB. Now when I flip the switch, the output changes to automatic mode and the output automatically follows the voltage that's dialed. So if I dial it to 5 volts, all the LEDs come on, and if I dial it the other way, all of them turn off. The final feature that I'd like to highlight before I get into how this circuit works is the I2C feature. This Arduino Nano reads the 7-pin output, and then it's available on the I2C bus using the slave mode of the wire library. Now for demonstrative purposes, this Nano reads that value over I2C and plots it on a serial graph. So here's what that looks like. So as we can see, as I dial the potentiometer, the value updates. If I go down and up, it follows. And we can switch to the serial monitor. I've connected this DMM, and we can see that the voltage follows the reporter value, and it's pretty close. So we see 3.18 on the DMM, and we see 3.19 or 3.27 on the serial monitor. Again, I'll do it again, 4.07, we see 4.09, which is very close. So now let's get into how this circuit works. So I've already gone over how the R2R ladder and comparator part of this project works. So I'm going to assume that that is already understood. So the first thing to understand about this stage is that these flip-flops are all wired in a way that on each clock cycle, the next output goes high. So after the first clock cycle, Q0 goes high, then Q1, then Q2, then Q3, all the way down to Q7. So when the device is first turned on, the comparator is outputting a 1 because the R2R ladder has a 0, which means this AND gate is on because one output is connected to 5 volts and the other output is connected to Q, which is controlled by the output of the comparator. So the MSB goes high. Now if the comparator stays high, this flip-flop stores a 1, and each flip-flop here can only store a value once because its clock is controlled by one of these Q lines, which only turns on once, and then it never switches until the next sample. So it goes through bit by bit. When each Q value goes high, it allows the AND gate to act as a mask. Since this is a 1 on the first clock cycle, the value outputted by this flip-flop is going to be echoed through. So if that's a 0, that becomes 0. If that's a 1, that becomes a 1. And this process repeats for each bit, and the value of that bit is either set or not set from the comparator and echoed into the D flip-flop. Now at the end, all these values are stored into this bank of D flip-flops. So and when Q7 goes high, which is the last clock cycle of the sample, this bank of flip-flops updates to the values stored in all of these, and then that is echoed to the parallel output. Now in automatic mode, when Q7 goes high, it's inverted, and then it automatically clears this bank of D flip-flops, which starts the sampling process again immediately. In manual mode, it waits for the start line to go low, and then it samples again. So that's how this project works. Thank you so much for watching, and thank you to Mitsuru Yamada for his schematic.